This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing certain exercise problems in mode of heat transfer, that is based on conduction, convection and radiation process. A conduction is the process of flowing heat energy from a body which is at a higher temperature to a lower temperature. That the heat energy always flows when the temperature difference that is existing between the two bodies. These two bodies should be in contact with each other. Otherwise, the heat energy also which flows from one region of a body to other region is called conduction process. The magnitude of heat energy that flows in a body by using conduction process is given by the equations that is called Fourier's law heat conductions, which is given by Q is equal to minus of K into A into dt by dx, where K is representing the thermal conductivity of the materials. If the K is the maximum, that is treated as a conductor now. That means which allow the flow of heat energy through it. When the K is the minimum or the zero, it is called a bad conductor, which does not allow to flow the energy through heat. Generally, these are called insulators. And the Ka is representing the area of the cross section through which the energy flow is taking place. dt by dx is the temperature gradient. dt is representing the difference of temperature between the two regions, and dx is representing the thickness of the object or the length of the object. But mostly dt by dx is treated as a temperature gradient, since the energy flowing from higher temperature lower temperature, that means the gradient is equal to T2 minus T1 by dx. Generally it is used now. It is a negative values, hence the temperature gradient always said to be only the negative now. And Q is the amount of heat energy that flows. Generally it is measured in watts. dx, that is the thickness in meter. dt, that can be represented in Kelvin or degree of centigrade. But here in most of the problems we are now taking that values in degree of Kelvin only. The heat transfer which is taken by convection process, that is generally it is happen in gases as well as the liquids, or the energy which is flowing from the liquid to the contact surface of the object now, that is solid, or from the surface to the again to the air or liquid. Generally the heat transfer that taking place by the mode of convection. So the relations which give the flow of energy is given by Newton's law of cooling. It is expressed as Q is equal to H into AS Tx minus Tf, where Q is representing the amount of flow of energy and H is representing the coefficient of heat transfer coefficient in convection process or coefficient of convect, and A is representing the area of the cross section. Ts is representing the temperature of the solids, that's the higher temperature. F is representing the air temperature of fluid now. That means this equation here, the symbol is representing now. T is representing the just nothing but temperature of the solid which is having in contact with the fluid, and F is representing, Tf is representing the fluid temperature. These are represented in Kelvin only. The radiations, it is the process of flow of energy from higher temperature to lower temperature by the radiation process. The amount of heat energy that flows it is given by Stephen-Boltzmann law. According to this law, the amount of heat energy that flowing is given by EB is equal to sigma into A into T to the power of 4. Here, sometimes it is also multiplied by F now, that is called shape factor. The shape factor is representing what is the shape of the object or which inclination it is kept with respect to the other object now. So here, where AB is representing the energy emitted or radiated per unit time now, which is generally measured in watts only. A is representing the surface area in meter square. T is the temperature of the hot body, and sigma is equal to Stephen-Boltzmann constant, which is equal to 5.67 into 10 to the power of minus 8 watts per meter square per degree Kelvin. This is the equations which give the amount of energy that is radiated, but nothing but we cannot use the words, it's nothing but to reaching other object now. So it is given by sigma into A into T to the power of 4. But when the two temperatures that exist now, this equation can be modified as now, that is Q is equal to, as per the radiation is equal to F, already I told it is the shape factor, into sigma into A. We can take T1 to the power of 4 minus T to the power of 4. This is the equation generally applicable for measuring the flow of heat energy by using radiation process from higher temperature to lower temperature. Okay, based on these three modes, we are having here certain problems. First one, determine the heat flow across the plane of wall 10 centimeters thickness with a constant thermal conductivity of 8.5 watts per meter per degree Kelvin when the surface temperatures are steady at 100 degrees centigrade and 30 degrees centigrade, and the wall area is 3 meters square. Also find the temperature gradient in the flow directions. First of all, we have to identify what is the given data in the problems. Here, the air temperature is represented here as a T1, which is equal to 100 degrees centigrade, and T2 is equal to 30 degrees centigrade. Thickness of the wall is equal to 10 centimeter, but it can be represented, should be represented in meters only, which is equal to 0.1 meters. Thermal conductivity is given 8.5 meters watts per meter per degree Kelvin. Wall area is given, that is the area of the cross section from which heat energy is flowing, is equal to 3 meters square. Okay, according to the conduction process, Q is equal to K into A into T1 minus T2 divided by L. By using these relations, K is equal to 8.5, A is equal to area of the cross 3, and 100 minus 30. This T1 and T2, while determining this flow of energy, you can convert it into Kelvin or the centigrade, should get the same value. Hence, 100 minus 30 divided by thickness, it is expressed in terms of meters 0.1. So, finally we got this value is equal to 17,850 watts. So, it can be expressed as again 17.85 kilowatts. Here the temperature, the second part is the temperature gradient now. Temperature gradient generally it is expressed as dt by dx only. It is always a negative value. It is equal to temperature gradient is equal to dt by dx with negative, which is equal to dt means nothing but represent temperature difference, that is 100 minus 30 divided by thickness is equal to 0.1 millimeters, that is 70 divided by 0.1. It can be equal to 700 degree centigrade per meter. Or you can measure just by using the equations. So Q is equal to K into A into dt divided by dx also. From this relations, dx is equal to q divided by ka. By substituting the values of q already we determined, which is equal to 17,850 divided by k is equal to 8.5 divided by a is equal to 3. It gives a minus of 700 degree centigrade per meter. Okay, this is our answer. The problem number 2, determine the heat transfer by convections over a surface of 0.5 meter square area if the surface is at 160 degree centigrade and fluid is at 40 degree centigrade. The value of convective heat transfer coefficient is 25 watts per meter square per degree Kelvin. Also estimate the temperature gradient at the surface given K is equal to 1 watts per meter per degree Kelvin. So, in the given data in the problem is the surface area is given A is equal to 0.5 meter square. The inner temperature is given, that means at the outlet it is given 160 degree centigrade. Outside is equal to T2 is equal to 40 degree centigrade. Convective heat transfer coefficients, generally it is expressed as in H, is equal to 25 watts per meter square per degree Kelvin. Thermal conductivity is given 1 watts per meter per degree Kelvin. Here heat transfer by the convections, because here the heat energy is flowing by using convection process, which is given by H into A into T1 minus T2. Okay, from this relationship we got H is equal to convective heat transfer coefficient equal to 25. A is equal to area of the cross section 0.5. Temperature difference 160 minus 40, which is equal to 1500 watts, 1.5 kilowatts. Since in order to determine the temperature gradient, here the energy is flowing with the steady state, that is the amount of energy which is received by convection process is equal to the energy transferred by the conduction process. Hence, the Q value remains constant. In order to determine the temperature gradient, that is we require dt by dx only now. Hence, Q is equal to, according to the equations, K into here T1 minus T2 divided by length or the thickness, which can be written as K into dt by dx. Here Q values is given already. From this relation we can take it as here dt by dx is equal to gradient, temperature gradient, which is equal to, that means dt by dx is equal to Q divided by K into a. Generally it is expressed in negative, so negative is there. Where Q is equal to that amount of energy that is transferring, which is given already we measured, it is equal to 1500 watts now. That is 1500 divided by K equal to thermal conductivity. The value of thermal conductivity is given 1 watt, that is 1. Area is given 0.5 now. From this relationship we got this values is equal to, on substituting, we got it is equal to minus of 3000 degree centigrades per meter. Here problem number 3 now. A surface is at 200 degree centigrades and has an area of 2 meters square. It exchange heat with another surface B at 30 degree centigrade by radiation process. The value of factor due to the geometric locations and emissivity is 0.46. Determine the heat exchange. Also find the value of thermal resistance and the equivalent to convection coefficient. Here, according to the Stephen-Boltzmann law, the amount of heat energy that is transferring by the radiation process is given by F into A into sigma T1 to the power of 4 minus T2 to the power of 4. Where F is the shape factor, according to this problem, it is equal to 0.46. Given A is equal to area of the cross section, that is 2 meters square. T1 is equal to higher temperature. It is exchange heat another surface that is 200 degrees centigrade. T2 is equal to 30 degrees centigrade. So just I am writing once again the given data. Initial temperature, that is from which the heat energy is flowing, which is 200 degrees centigrade, which is equal to 200 plus 273, which is equal to 473 Kelvin now. Final temperature is equal to 30 degrees centigrade, which is equal to 30 plus 273, which is equal to 303 Kelvin. Stephen Boltzmann, which is equal to sigma 5.67 into 10 to the power of minus 8 is given. Surface area is equal to A, 2 meters square. Shape factor is equal to 0.46. Therefore, Q is equal to F into sigma into A, T1 to the power of 4 minus 2 to the power of 4. And substituting these values in this equation, we got 0.46 into 5.67 into the power minus 8, this Stephen Boltzmann constant. Surface area 2 into 470 to the power of 4 minus 303.4. On simplification, we got this value is equal to 2171.24 watts. So the thermal resistance is equal to Q is equal to delta T by R now. So from this relation, so R is equal to, we can take it as delta by R. This value is equal to here now 0.07829 degree centigrade per watts. Here problem number 4. A slab 0.2 meter thick with a thermal conductivity of 45 watts per meter per degree Kelvin receives heat from a furnace at 500 Kelvin both by convection and radiation. The convection coefficient at the value of 50 watts per meter square per degree Kelvin. The surface temperature is 400 Kelvin on this side. The heat is transferred to the surroundings at T alpha 2 both by convection and radiation process. The convection coefficient on this side is 60 watts per meter square per degree Kelvin. Determine the surrounding temperature. Assume F is equal to 1 for radiations. Okay, the given data in the problem is here this is the temperature representing this hot fluid temperature. The hot fluid temperature is represented according to the problem as T alpha 1. According to this problem, it is having just 500 degree Kelvin. This is a surface having contact with the hot fluid now. Because of contact with the hot fluid, the temperature of this side is raised up to 400 degree Kelvin. That is 500 is representing the hot fluid temperature, 400 is representing the temperature of the wall which is having in contact with the fluid. So here from T1 to T2, that is the heat flow is taking place in a slab, that is by using conduction process. From T2 to again the surrounding T alpha 1 now, alpha 2 now is taking place. All T alpha 2 is representing the temperature of the surrounding area. Assume here environment atmospheric air. Here that because of this temperature, again the radiation as well as the convection process is taking place to flow the energy from the outer surfaces. That means here now, in first case the heat energy is flowing from hot fluid to the surface by using convection as well as the radiation process. In a solid, again conduction process. Again from the surface of the solid to the environment, that is atmospheric air, by using convection as well as the radiation process. So here 3 modes of heat transfer is taking place, but it is a steady state condition. That means the amount of heat energy flowing in each state, that is in each mode, that remains constant. Okay, the given data in the problem is the thickness of the slab is given 0.2 meters. Thermal conductivity K of the material is equal to 45 watts per meter per degree Kelvin. Fluid temperature is given 500 degree Kelvin. And the coefficient of convection is given 50 watts per meter square per degree Kelvin. The surface temperature at inlet, here it is represented as T1, which is equal to 400 Kelvin. Convection coefficient of hot fluid is given 60 watts per meter square per degree Kelvin. And the shape factor is equal to 1 at the inlet. Surface temperature at the outlet is equal to T2. We have to determine that values. Let the surrounding temperature be T alpha 2 now. Surface area is equal to 1 now. First of all, we are taking here now, in steady state condition, the amount of heat energy that is flowing from hot fluid to the inlet surface of the object by using conduction and convection process, it can be expressed as F into sigma into A into T alpha 1 to the power of 4 minus T1 to the power of 4. It is by the radiation process plus convection process H into T alpha 1 minus T1. Here A is also there now, but A is equal to 1 according to this problem. And substituting these values in this equation, we got F is nothing but equal to 1. Sigma is equal to 5.67 into 10 to the power of minus 8, Stephen Boltzmann constant. And area is equal to 1. T alpha 1 is equal to 500 to the power of 4. Here T1 400 to the power of 4 plus here H is equal to 50 and T alpha 1 is equal to 500, T1 is equal to 400. On simplification, we got this value is equal to 7092.2 watts. This is the amount of energy that is flowing from the hot fluid to the inner surface of the solid or the slab. Similarly, the amount of heat transfer through the slab, that is by using conduction process, is given by K into A into T1 minus T2 divided by L now, where Q is the nothing but steady state condition, the amount of heat energy that remains constant. A is the thermal conductivity of the materials, A is the area of the cross section, so T1 is representing that is inside temperature of the wall, that is which is having in contact with the hot fluid, and T2 is the lower temperature that is outside of the wall, which is having in contact with the atmospheric air now. L is equal to the thickness of the slab. And substituting the values, that is Q is equal to 7092.2 equal to 45 into 1, 400 minus T2 divided by 0.2. From this relationship, we can determine the T2 value is equal to 368.243 degree Kelvin now. Okay, on the other side of the slab now, when we are taking now, that is this side we are taking. The contact temperature is equal to T2. Already according to this problem we got it is equal to 368.243. T alpha, this we have to measure now. Q value remains constant, but the heat energy is flowing from the surface of the slab to the air by using convection as well as the radiation process. Hence, the amount of heat energy flowing from the outer surface to the air, it can be represented as now F into sigma into A into T to the power of 4 minus T alpha to the power of 4 plus H into T2 minus T alpha 2 now. On substituting this value, Q remains constant 7092.2, which is equal to 5.67 into 10 to the power of minus 8 into 1, again which is equal to 368.43, this is equal to T2. T alpha 2 we have to determine by using this equation to the power of 4 plus for convection process H is equal to 50 is given 368.43 minus T alpha, this value again we have to measure. From this relationship we got to that is 5.67 to the power of minus 8 T alpha 2 to the power of 4 plus 50 T alpha 2 is equal to 16,056 now. By solving these problems by trial method, we got T alpha 2 is equal to 263.3 degree Kelvin. This is our answer. Here problem number 5. A surface is at 200 degrees centigrade and is exposed to surroundings at 60 degrees centigrade and converts and radiates heat to the surroundings. The convection of coefficient is 80 watts per meter square per degree Kelvin. The radiation factor is 1. If the heat is conducted to surface through a solid conductivity, 12 watts per meter per degree Kelvin, determine the temperature gradient at the surface in the solids. So the given that in the problem is given here now. T2 is equal to 200 degrees centigrade, which is equal to 473 degree Kelvin. Surrounding temperature T alpha 2 is equal to 60 degrees centigrade, which is equal to 273 plus 60, it is equal to 333 degree Kelvin. Convection coefficient H is equal to 80 watts per meter square per Kelvin. Thermal conductivity equal to K is equal to 12 watts per meter per Kelvin. The heat transfer from the wall Q is given by here heat convected plus heat radiated now, which is equal to F into sigma into A into T to the power 4 minus T alpha to the power 4 plus H into T2 minus T alpha 2. Where F is equal to the shape factor, which is equal to 1 already given now. Sigma is equal to Stephen Boltzmann constant, which is equal to 5.67 into 10 to the power minus 7. T2 is equal to here temperature is given 473 to the power 4 minus 333 to the power 4 now. This on solving this problem, so we got 80 into 373 minus 333. Finally, we got this value is equal to 13,340.9 watts. Here problem number 6 now. A surface is at 200 degrees centigrade and is exposed to the surroundings at 60 degrees centigrade and converts and radiates heat to the surroundings. The convection coefficient is 80 watts per meter square degree Kelvin. Let T be the temperature of the wall at the inlet T1. The amount of heat transfer through conduction per unit cross section is given by Q is equal to minus of Ka into T1 minus T2 divided by L minus into K into A is equal to 1 is given T1 minus T2 divided by L, which is equal to minus of 12 T1 minus T2, it is defined as the temperature difference divided by thickness. This dt divided by L, it is called to temperature gradient. So minus of 12 into dt by dx. Okay, in these problems we have to calculate the temperature gradient for the wall. So since the system is steady state conditions now, the Q value is given already 13,340.9, which is equal to minus of 12 dt by dx. Okay, from this relationship we got to dt by dx is equal to 13,340.9 divided by 12, which is equal to 1111.7 degree centigrade per meter. This is known as temperature gradient for the given solid. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.